An equation that shows up in the book but we haven't done much with yet is the following, and so we started out, let's go back to our definitions. The energy of a single particle was gamma mc squared, and that includes both the kinetic energy and the rest energy, right? And we have the momentum of a particle. We'll take the magnitude here. That was gamma mv. So take magnitudes. It looks like they ought to be somehow related. There are all these gammas and these m's and these v's floating around. And in fact, if you do a bunch of algebra, and there's actually a homework problem in the end of the chapter that suggests that you do this, you get to the following relationship. You get the particle energy squared minus the magnitude of the momentum times the speed of light squared is equal to the square of the rest energy, mc squared squared. And that's actually just algebra. It just so we're using this notation again where we're saying that we're just using the shorthand that the magnitude of a vector is just the vector without any the letter without any decorations. And that's actually just algebra. It's a true relationship, but it raises an interesting question. It looks like if there were a particle whose mass was 0, it could still have energy and momentum. Because if its mass was 0, this would reduce to the total particle energy squared is equal to the magnitude of the momentum times the speed of light squared. If m equals 0, yeah. Well, the way we've written momentum does have mass in it. But in fact, it actually does turn out that there can be particles that have momentum and energy, but 0 what we call rest mass. That is, the mass in this equation here is the mass you'd measure of something sitting at rest. What if there's something that can't be at rest? And so it doesn't have a rest mass. But empirically, if you let it hit something, it transfers momentum. You look at collisions. Well, there are such particles. They're hitting you right now. They're called photons, and they're particles of light. So a photon is a particle that can do nothing except travel at the speed of light. That's it. It's a packet of energy and momentum traveling at the speed of light. It has only kinetic energy. And how do we know this? Well, because it can transfer energy to other systems, and we can measure it. It can transfer momentum to other systems. We can measure the momentum transfer. So photons are very interesting things. They act in all other ways just like particles, except they don't have any mass. So that means that the way we've been writing momentum isn't as general as we need it to be, and actually this equation for magnitude of momentum anyway is probably going to give us a better handle on the momentum of a particle like a photon. Now, photons are part of our daily life. We have photons coming from light, these fluorescent lights. We have photons coming from the sun. These are photons whose energy are such that they interact well with the molecules in our eye that detect photons in the range we call visible light. But there's photons that have more energy than that, like X-rays or gamma rays, yeah. And there's photons that have less energy than that, microwave, radio waves, infrared. So, and it just, they're all photons. It just happens that our eye is only sensitive to a particular range of it. So we have to use other detectors. And so it's possible that we could actually have a reaction of the following kind. We could have something like we take an electron and a positron. A positron is, I think we've mentioned them before, it's a particle that has the same mass as an electron, all the characteristics of an electron, but it's got a positive charge, and it's what we call antimatter, because if a positron and electron actually come together, they annihilate. That's right. They just boom. And but we have this rest energy here. So we have the mass of the electron. So suppose they start far away at rest. We've got this mc squared here, and we have this mec squared, and yet we're going to, well, it better be something. 2 photons, that's right. So we end up with no mass, no, quote, mass at all, but we have 2 photons, and they happen to be photons of the energy we call gamma rays. So just to be confusing, we're going to write gammas to symbolize them, but we'll put their photons. And these only have kinetic energy, so all this rest energy got converted into kinetic energy, and we start to think they're really the same thing. Mass, energy, they seem to be interconvertible. And so if we think about it that way, it's helpful to think about what happens when we form multi-particle systems like an oxygen atom, for example. So suppose we have a chemical reaction you all know about and love. We have, let's do it this way. We have 2 oxygen atoms. They react to form an O2 molecule, which is what we've got floating around in the room, so that's why we can all breathe. So let's think about what happens to mass when we have this reaction. So here's basically what we've got. We've got an oxygen atom and another oxygen atom that produces an oxygen molecule. And there's a little energy that's left over. So we get a photon. And this photon is about a 5 electron volt photon, and that's just out of the range that our eye can see. Our eye can see visible photons. It's something like about 1.8 electron volts to about 3 electron volts is the energy range that the molecules in your eye are sensitive to. So this is probably ultraviolet, a little bit above that. So let's think about what happens. We have the rest energy here. So we've got a mass of an oxygen C squared. We've got a mass of an oxygen C squared. So let's consider 2 oxygen atoms that just drifted together and were just at rest and touched each other and reacted to form an oxygen molecule. So we didn't have any extra kinetic energy. And now we have the rest energy of this, but we've got this extra photon energy. It looks like this rest energy has to be about 5 eV less than the sum of those rest energies. Now, electron volt isn't a lot of energy, but it's some. Yeah, they're at rest. Let's not worry, but that just complicates it. We want to consider the simplest situation where we don't have to worry about kinetic energies. Okay, so they're just at rest. They're just at rest touching each other. They react to form an oxygen molecule. Let's think about masses here. We want to think about what's the mass of an oxygen molecule. Now, this is a multi-particle system, right? So it's got these two, so it's a little more complicated. So basically we can draw graphs. So we've got this potential energy. We'll see in a few minutes that the potential energy curve for two neutral atoms interacting is a little bit more complicated than just the electric potential energy curve, because we've got all the protons and we have all the electrons, and they're in slightly different locations, and so it ends up, the potential energy curve we'll see ends up looking kind of like that for two neutral atoms. And this is a bound system, right? So an oxygen molecule is a very happy camper, and so we get some K plus U that's negative. But it's interesting to say, what about the rest energies? Well, on this scale I can't really draw it because the graph would have to be incredibly high, many stories high. So we're gonna draw a graph that's not to scale here. But basically what we've got is, if this is energy, this is the rest energy of one oxygen atom. And here's the rest energy of another oxygen atom. So that would be the sum of the rest energies. But then we've lost this 5 eV. That went away as the energy of this photon. So it looks like what we've really got for the molecule is this total energy. That's 5 eV less. So this 5 eV, that's called the binding energy. And it's actually a negative number. It means, it means it's the amount of energy that's given off to form the bond, and therefore it's the amount of energy you'd have to put in to break the bond and separate the oxygen molecule back into binding energy. So then we sort of might ask the question, well, so here's this oxygen molecule at rest. What's its mass? Per mole. Per mole. So we could say, well, this total energy, since it's at rest, must be something like the mass of the O2 molecule C squared. So actually what we call the rest mass of this multiparticle system is slightly less than the sum of the rest masses of the two things that made it up, that reacted to form it. So we start seeing that the mass of one particle is real easy. When you get particles stuck together, then you start going, it's not the sum of the things that made it up. So this is this is actually going to be less than the masses of the rest energies of the things that created by about 5 eV. So that's called binding energy. And notice that it could come off in the form of a massless but energetic photon by a small amount. So 5 electron volts. No, they have energy. No, there isn't conservation of mass. No, and that there actually isn't conservation of mass. What there is conservation of energy, but it can flow from kinetic energy to potential energy to rest energy and back. And so this is going to be a very difficult thing to measure. You can't measure it on ordinary balance, but it's there. This small difference is actually there. And so there isn't conservation of mass. What there is conservation of energy. And where this really impacts us is in nuclear reactions, where This is a very tiny amount in this kind of chemical reaction where just electrons are rearranging. But when you get rearrangements of nuclear particles, the energy difference is a lot more. You get energy that was present as rest energy converted into kinetic energy of things that fly out and heat water and other things, and so it's just a bigger amount, so it's easier to measure. But the principle is the same.